Okay, everybody, I guess we'll get started there now. It's 11 o'clock. So this week for our seminar series, we have Meghan Donovan. So Meghan is a fisheries technologist with the Center for Sustainable Aquatic Resources. She did her honors on sexual dimorphism in Caitlin and her master's on sexual selectivity and acoustic honest signaling in the round goby. After her master's work on fish bioacoustics, she accepted a contract position working on reproductive acoustic signaling in lake sturgeon, a long-lived species that is threatened and little is known about their reproduction. She has experience with recording sounds using a hydrophone, both in situ and in tank environments, as well as using speakers for playback experiments. She has worked aboard trawlers, seiners, crab and lobster vessels, and is here today to talk to you about light and sound in the fisheries. So with that, I will pass it on to Meghan.
Okay, thank you for the introduction, Rihanna. Can everybody hear me? Good? Okay. Today I'll be talking about light, sound, and how we can use them in the fisheries, as well as a little bit about the light and sound use at Caesar. So, as a short history of light use, humans have used light in fisheries for hundreds of years. This started as bonfires as close to the water's edge as possible. And once fish had congregated, people would walk into the water with a beach seine, encircle the fish, and drag them to shore. Eventually, the use of torches allowed people to mobilize light, taking it out into the water with them. So fishers would walk into the water with a torch and either a spear or a net, and they would attract fish that way and capture them as they came close enough to sort of spear or net them. The advent of electric light has allowed this to occur at a large scale, and especially when fishing at night. Um, this exploits a natural phototactic behavior in fish. For example, you can see in the picture on the left, there is a squid boat with green lanterns hung out over the water. And the next picture is a herring seiner right here in Newfoundland. And they've pointed their deck lights out over the water. And this helps bring the herring upwards and within range of the purse seine, which then scoops the fish up and they pump the fish aboard into their hold. Finally, we have a group of ice fishers, and they actually have their lanterns hung directly above the hole, and that attracts whatever their target fish is, and they would fish as normally. When it comes to modernizing underwater light, there is a huge diversity of products available. This is just a sample of the products that are already highly commercialized. You could go out on Amazon or to a local store even and purchase some of these yourselves. There's things such as the hook and line fishery, with just glow sticks. You snap them, you put them into a specialized lure, and you catch fish that way. Glow sticks are also very common in the long-line swordfish fishery to attract swordfish much more readily than just bait. There's things like submersible lanterns, where you drop the lantern overboard and the battery is on deck, so you have this long cable going down into the water. There's also water-activated LEDs that you can attach to lines or traps. So, you hook the little LED right onto whatever you want it on, and once it hits the water, it turns off. Once it's dry, it turns back on, or it turns back off. I got those backwards, sorry. There's also on the top right, you can see a Lingard Pitman light designed to activate when water pressure increases. So these lights are pretty nifty. Once they are deep enough down in the water, the pressure actually turns them on. So light's being tried worldwide across dozens of fisheries, either to attract target species or to reduce bycatch. So before we jump into the use of light as a bycatch reduction device, I'm going to quickly go over the parts of the trawl in case anyone attending isn't familiar with this gear. So from the vessel at the surface, we have warp that leads all the way down to the doors. And the doors are these big, heavy metal, typically square um, doors. And they spread the net and allow it to fly. Um, the doors then lead to the bridles, which connect to the headline and the ground gear. The mouth of the trawl is made up of the wings and the bosom section between the headline and the fishing line. The fishing line is in turn connected to the ground gear. So down towards the escapement, down towards the cod end is typically where there will be an escapement panel or potentially a Nordmore grid, depending on the fishery that's being targeted. Um, for example, the shrimp fishery, uh, the Nordmore grid is mandated for the shrimp fishery. Anything that goes past this area would wind up in the cod end. So for light as a bycatch reduction device, individual species reactions to light can often be unpredictable. So determining how behavior changes in the presence of light is crucial. It's important that a bycatch reduction device not affect the capture rate of the target species, as this can actually lead to increased fishing effort, which ultimately would be more detrimental potentially. So, Southworth et al. Just observed a reduction in whiting by 88% and haddock by 58% above 50 meters, as well as a reduction in haddock of 47% and flatfish by 25% between 50 and 100 meters with the use of light. So those fish were actually driven away by the presence of light on the trawler. Ellie et al. Show that in the Nephrops or Norway lobster fishery, LED lights create a positive phototactic response from multiple species caught. So in this study, they had a separator panel in the middle of the trawl, um, sort of horizontally. So they tried lights below as well as lights above, and whichever side of the net the lights were on, a lot of species went to. Unfortunately, this included the Norway lobster itself. And so in this case, the bycatch reduction device would not work. Knowing the reactions of the species you're trying to avoid catching is very important when deciding where on the net to attach the light. As an example, let's dive into bycatch within the shrimp fishery. So Lomelli et al. In 2018 found that LEDs on the fishing line promoted the escapement of eulichin, and small rockfish without affecting ocean shrimp capture. Alternatively, Hanna in 2015 demonstrated that the addition of lights to the grid itself actually increased the capture of eulichin. So placement of light definitely matters when dealing with the same species. Larson, similarly, found no effect of LEDs attached to the Nordmore grid on the bycatch of small fish during the deepwater shrimp fishery. In this case, there was no change with or without light, so it's likely that small fish either didn't respond or didn't have the energy or strength required to escape before capture. So depending on the species that you're trying to um, reduce the catch of, you really have to take into consideration the behavior of not only your target species, but also of the bycatch species when placing your bycatch reduction devices. Moving on to how light can be used to capture fish, before I get ahead of myself and talk about the local use of light, I'm going to introduce one of our friends here at Caesar. This beautiful little guy is the snow crab. The legal size here in Newfoundland is 95 millimeters in carapace width. So the thickest area of the shell needs to be at least 95 millimeters in order for this guy to be brought in. So this is a male-only fishery, as the females never reach this size. They stay very small, and in Newfoundland we catch them in large Japanese-style conical pots. And the fishery itself is pretty clean. It has relatively little bycatch, and what little bycatch there is tends to be undersized snow crab. Even the undersized snow crab tend to be near legal size, because anything smaller simply walks out of these stretched meshes or falls out upon haulback. So you might see these conical pots hanging around harbors in Newfoundland locally. They're typically orange in Newfoundland, but you'll occasionally see green ones. And a lot of these green ones are not your traditional pot. They are luminescent netting created by Euronet Company in Portugal. It is produced commercially and available locally. And the green twine has a single luminescent fiber woven into it. This fiber absorbs ultraviolet radiation and will glow for a short period of time after deployment. Now, this picture is really for demonstration purposes only. It's not actually this bright in real life. And I'm sure most of you had glowing toys as a kid, or maybe those glowing star stickers that you'd stick to your walls or ceilings. It's very similar to that sort of glow. It's fairly dull, but um, in the darkness of the water, where an animal is highly adapted to see any amount of light, I'm sure that snow crab can pick up that light quite readily. The netting itself is very cost effective compared to the more expensive LEDs. There are no batteries to replace. There's no extra wrangling on commercial settings to get extra lights attached to the trap, so it doesn't slow down the commercial operation, which is probably part of why these these traps have been such a huge success in the commercial fishery here in Newfoundland. So when we talk about the luminescent decay of the traps, the glow itself isn't very long lasting. It's only visible to the human eye for not even a full hour, and perhaps a little bit longer to snow crab that are adapted to life in the relative darkness of the ocean. The pot's charged with sunlight, even on a cloudy day, so no special equipment is needed aboard the commercial vessel, which are often quite tight on available space. And you can see on the graph that while sunlight has a lower immediate intensity than straight UV light, it does last for roughly the same amount of time and potentially even stays a little bit brighter for a little bit longer. So the initial light source is a strong enough attractant that the catch crew effort is substantially increased. Now, these figures are for different areas, but they are both inshore areas and both have historically lower catch rates than the offshore. The figure on the left shows a 55% increase in catch rate for legal-sized crab, and on the right, it shows a 22% catch rate, increase in catch rate for legal-sized snow crab. Now the difference here is a 1-day soak time for the 55% increase, and for the 22% increase, it's a 9-day average soak time. So even with the 9-day soak, you're still seeing the initial bump of the snow crab. Now, there was also a small increase in sublegals for the 9-day soak, but there was no increase seen for the 1-day soak of sublegals. So we definitely need to do more work to determine the effect of glow on sublegals. But with such a large increase in legal catch rate, even the observed increase in the catch rate of sublegals, with the overall increase, you can imagine the number of sublegals is actually less with the experimental pots than with the traditional pots. So using these pots actually works not only as an attractant to catch greater rates of legal-sized snow crab, it also ultimately reacts as a bycatch reduction device because you're catching your quota much faster with the glow pots than without. So why does light attract fish? In most cases, the reason is not known, unfortunately. But possibilities include positive phototaxis, where the organism orients itself to the source of light, a preference for the light intensity itself, where the organism wants a certain light level, possibly following its diel movement pattern according to the light intensity, the investigatory reflex, where an animal wants to examine a novel object, feeding, where the animal could potentially consume the light source, or schooling, where animals just like to be close together, and they might school around a light source so as to better see each other. These possibilities are often confounded. For example, cod increases in the presence of light, but the light itself is not the attractant. Krill are attracted to the light, which in turn affects cod. The intensity of the emitted light doesn't seem to have an effect on the attraction of more krill, but it does certainly make them more active. You can imagine krill bouncing around, very tempting for cod to also want to enter the trap. So, talking about positive phototaxis, when we are working with night fisheries, a lot of the time positive phototaxis is the suspected mechanism. For example, the herring purse seine fishery or the squid fishery. Both herring and squid rise in the water column at dusk, suggesting a preference for dusk light intensity. Vessels take advantage of this natural movement by prolonging it with above water lighting. These animals are positively phototaxic and have a preference for dusk light intensity. So the fish are drawn upwards towards the light, mimicking their diel movement. And for example, you can see on the left is a school of herring on an echo sounder, and the purse seines flooded the area with light. And so on the right, you can see that exact same school rose up in the water column and allowed their own capture by the purse seiner, which then scoops them up and pumps them into the holes. In terms of preference for light intensity, light detecting organs like eyes have spectra within which light is visible. Humans typically refer to colors as the visible spectrum, but this doesn't apply to all animals. Plenty of animals see more, and many see less than we as humans are capable of. And for all animals, different colors will have different intensity thresholds. So some colors are seen better than others. The ability to see certain colors better than others comes in handy when water attenuates light, basically absorbing it and making it no longer available to the animals in that environment. And so at depth, everything sort of takes on a blue-green hue. This example shows cod that are acclimated either to light, as seen on the left, or dark, as seen on the right. Cod that have been light acclimated see on the lower end of the visible spectra better, so they see blues and purples better than cod that are acclimated to the dark, which see better in the blue-green range. So this is very useful as light attenuates and sensitivity to certain hues becomes more important. And the ocean is absolutely full of light. It's a natural fixture in the ocean environment. It occurs across a diversity of clades as bioluminescence. So this includes things like dinoflagellates, polychaetes, hydrozoans, and fish. Far from the black abyss that we think of as the deep ocean as humans, bioluminescence is globally observed. It is extremely prevalent, and our eyes are simply just not adapted to seeing all of these tiny specks of light. Locally, in Newfoundland and Labrador, bioluminescence peaks in the spring due to dinoflagellates. So if you've ever gone out for a walk along the beach and disturbed some rocks at the edge of the water, you'll see blue sparkle up, and that's dinoflagellates. As a general example for deep areas of the Atlantic Ocean, bioluminescent organisms are located at all depths, right down to 3,000 meters. So again, very prevalent, and as long as there are animals that have eyes, there are animals making light. On the snow crab fishing grounds off Newfoundland and Labrador, Parzanini et al. Found that lanternfishes were the predominant pelagic species found in bottom trawl in deep waters, and several other organisms that were bioluminescent were also caught. And with all organisms, bioluminescent ones are also edible, so it pays to be able to see them. Switching to sound now, Jacques Cousteau famously referred to the ocean as the silent world. This is because until very, very recently, humans had no way to listen to underwater sound. This makes the use of sound in fisheries fairly novel compared to light. Historically, there's still been harvesters who use sound in fisheries. Some fishers in Newfoundland believed putting metal on buoy lines would cause whale to avoid the lines. They believed that the clanking metal would be heard and act as enough of a deterrent to prevent or decrease whale entanglements. Similarly, lobster harvesters would occasionally crush up tin cans like pop cans and put them into their lobster traps, believing the rattle to help attract lobsters. So many differences exist in sound transmission between air compared to water. The increase in speed from 332 meters per second in air to 1,484 meters per second in water means that sound travels immense distances in water compared to land, and it does so very, very quickly. The sound differential created a problem historically on how animals determined the direction of the detected sound. So on land, where sound is so much slower, we have time to hear which of our ears is detecting sound first. In water, the massive speed increase causes sound to reach both ears at approximately the same time. So, for a long time, there was this huge debate on if animals could hear at all. They certainly wouldn't be able to determine the direction that the sound source was coming from because their ears were too close together. Animals, of course, combated this with highly adapted hair cells. So they are very, very highly adapted to their environment using these hair cells in the inner ear. So certain groups of hair cells only fire when they're bent a certain direction. And they're arranged in all these different patterns in huge numbers of groups. And if some of them are bending in one direction and some of them are bending in another, while others don't bend at all, that allows for the determination of directionality. So humans had to catch up to animals. As humans adapted to listening to sound in air, we can't really detect sound underwater reliably. We have to rely on highly specialized tools in order to listen to aquatic sound. These tools are hydrophones, which detect vibrations in water, and geophones, which detect vibrations in solids. Sound detection by fish relies on the two different types of sound motion: sound vibration, particle motion, and the actual propagating pressure waves. So up close, fish typically use this particle motion, and this is picked up by the octavo-lateralis system or the lateral line with those hair cells. There's also propagating pressure waves, and this pressure wave is typically picked up by animals that have air in their body, or the swim bladder, for instance, in fish, which acts as a resonating chamber to detect pressure. The closeness of the swim bladder to the inner ear, in turn, acts as a sort of resonating chamber and allows that sound pressure to be picked up by the inner ear. So you can see on the diagram on the right, um, several types of communication are shown. Um, Two individual fish in A are communicating. Typically, this communication happens quite close by. Um, in benthic communities, for example, it would typically be within 3 meters or so. In pelagic fish, it can be a bit further, but even within 10 meters, a lot of these communication sounds have decreased. All of the sounds together, however, of various fish communicating, can act as a sort of homing signal for larvae to reach reef environments. And even at a distance of 10 kilometers or greater, larvae can pick up on these reef sounds and find an appropriate habitat to settle into. And just as with light, thresholds of hearing differ by frequency and animal. So fish typically hear lower frequencies, under 10,000 hertz, and marine mammals hear higher frequencies best, above 10,000 hertz. These ranges are also within the animal's vocal ranges, allowing animals to most easily communicate with one another. A recent dilemma has erupted surrounding the topic of aquatic hearing. So, sound production is documented in hundreds of species and suspected in many more. There's several types of calls produced by fishes, including alarm, agonistic, and courtship. Alarm calls are those that elicit a response by conspecifics, while distress calls are meant to dissuade the predator from attacking. The Atlantic cod, for example, will produce grunting calls when chased by a novel object or by a predator, and will continue to grunt when cornered and immobile. In the cod, these cues may be used as a warning to nearby conspecifics or as a means of attracting a secondary, larger predator potentially allowing escape by the cod while the initial predator deals with their own predator. A more clear alarm signal exists in the long-spine scrollfish, where an encounter with a predator will cause the scrollfish to produce a staccato call, which either elicits retreat or mobbing behavior by nearby conspecifics. Now, sounds in the ocean are extremely varied. There's pops, grunts, hums, whistles, rumbles, clicks, and moans. And all of these sounds exist for a reason. Communication is extremely important. So that recent dilemma that I brought up is the effect of anthropogenic noise. Noise pollution is a very real problem, and anthropogenic noise has the potential to mask communication, disrupt natural behaviors, and force aquatic organisms away from vital habitat. Research is underway to determine the effects of anthropogenic noise on aquatic life, but findings are very mixed thus far. There has been found to be clear damage in confined fish close to a loud sound source. However, snow crab don't change their behavior, gene expression, or physiology when subjected to very loud seismic sound. So there's evidence both ways on sound having an effect on organisms. In lab settings, there has been temporary hearing deficits, but there's less evidence for effects on free-living animals to sustained noise. There's some evidence for behavioral avoidance to impulsive sounds. For example, cod have been found to react to the sound of trawl vessels at a distance of over 1 kilometer, and cod will actually dive in the presence of a trawl vessel. Similarly, Ona et al. Found some vessel avoidance for herring, but Popper, in turn, claims that it's unclear as to what these fish were actually responding to. So with some studies showing that certain animals do have an impairment of hearing and changes in behavior, and others don't, should we be concerned about the use of sound in fisheries? In most cases, the potential benefit is likely to outweigh the risks. Most studies showing negative effects on species rely on studying animals in tank environments, where sound does not act as it would in nature. As well, these sounds are often far above the scale of any wild organism would encounter. So you can imagine in a very small tank with an extremely loud sound source, that sound source doesn't really attenuate and go away. It just resonates. So it is extremely loud and it stays extremely loud, and the animal has no way of getting away from it. And they're typically placed very close to the sound source as well, which wouldn't really be happening in real life. So the question becomes, how can we, as humans, harness natural behaviors for our gain? Can we use sound as pest control, or bycatch deterrent, or alternative bait? And with how diverse the reaction of animals is, and how different each animal's sensitivity is to sound, the effects of the target sound on the target species needs to be determined before commercialization of devices. So we'll start with pest control. Acoustic lures were attempted as a means of slowing the spread of the invasive round goby in the Great Lakes. The round goby has invaded not only the Great Lakes, but several other water sources in and around North America, as well as Europe. This fish has parental males. You can see in the middle, he's quite a bit larger than sneaker males or females. And when he's reproductively ready, he turns black. The edges of his fins turn white. He finds a nice nest, and he starts to grunt. And the grunting is done to attract females because the male himself won't really leave the nest, and females can't easily see him when he's hidden away. So the male call was played from a speaker inside the trap, similar to the one that you see on the left there. Now, gobies clustered around these traps, but wouldn't go in. The traps themselves may have needed to be changed to allow for easier entry, or perhaps the fish, which is notorious for not being terribly clever, may just not have been able to figure out how to get into the trap. But on the plus side, in a way, the traps were still successful because predatory fish, like the smallmouth bass, was also attracted to the acoustic traps. And the predatory fish would hang out around the traps and pick off fish as they showed up. So these traps would have been very ideal for controlling the invasive population, as the acoustic signal largely targets reproductive females. And if you're removing reproductive females from the population numbers would remain low and slow the invasion. Moving on to acoustic deterrents, there's lots and lots of acoustic deterrents commercially available. The model I'm going to talk about today is the banana pinger, produced by Fishtech Marine. You can see why it's called the banana pinger. The pinger itself fits inside this sleeve. It's shaped like a banana. So, aptly named, the banana pinger has a long-lasting battery. It frequency modulates itself with various harmonics, and so animals that the pinger is targeting can't actually easily acclimate to them. Even after years and years of being in use, animals don't seem to get used to these pingers, which is absolutely fantastic. They attach easily to gear, and they're very durable, which is good for commercial settings. The pingers are available for dolphins, porpoises, whales, and pinnipeds, all of which have different acoustic thresholds that need to be taken into account for the deterrents to work. So if you have issues with different species as bycatch, unfortunately you need multiple different models, but on the plus side, you won't end up with marine mammals in your fishing gear. So there's been dozens of studies that show that bycatch decreases significantly when banana pingers are on gear. In a small-scale Peruvian driftnet fishery, there was a 37% decrease in small cetacean capture when using these pingers. In the United Kingdom, harbor porpoise detection rates within 100 meters of nets fell when using the pingers. And in gillnet fisheries in New England, California, and Oregon, the mandated use of pingers has actually seen a decrease in bycatch of 60%. So they work extremely well as a deterrent. Moving on to acoustic lures. Lures haven't actually been used very much as of yet. So this is part of my own work, and I'm using a old Russian paper by Tolstoganova. Tolstoganova herself recorded king crab feeding in Russia in 2002 and did a playback study where it was determined that king crab are attracted to feeding sounds. So you can see that, like the king crab, snow crab have a set of quite nasty looking grinding teeth in their mouth. You can see the teeth in that middle picture there, and they would sort of hold food and crush it and grind it between those nasty chompers. So the fact that their teeth are similar led me to believe that the sounds between such similar species as snow crab and king crab would also be similar. Unfortunately, I couldn't find any contact information for Tolstoyanova, so I recreated the sound myself in Audacity, which is a sound editing program. The model I use for my own research for the Acoustic Lure is produced by FT Tech, which is an Austrian company. Now, these are also commercially available. They have an internal rechargeable battery, which made it very ideal for a commercial setting. You just swap them out, and you can either charge them on board by sitting them sort of in a little cradle and they charge, or you can take them home and charge them, say, in your shed or your garage. These things are great because not only do they not have battery rate wastage because of the internal battery, they also have two color changing LEDs, a UV LED, and a speaker. They're fully programmable, so you can make blinking lights, you can change the sound, whatever you want to do. So I loaded up the synthetic king crab feeding sound, and we set out to do a commercial catch pre-unit effort study. Unfortunately, there was no effect on the catch pre-unit effort of snow crab using these acoustic lures. Not all acoustic lures will work, and certainly knowing an animal's sound detection capabilities beforehand is highly recommended. Very few crustaceans are actually believed to detect sound, despite the fact that they are arthropods like insects, and insects have an amazing capability for sound detection. So, why might this be that the acoustic lure didn't work? Well, perhaps snow crab don't hear very well, or perhaps snow crab can actually hear very well, and they can distinguish between conspecifics, like the king crab. Alternatively, perhaps it was the synthetic sound itself, and it didn't sound enough like a feeding sound. It might have been inappropriate to use a synthetic sound for this species. So more research on how snow crab use sound to interact with their environment is needed. My future work will focus on determining how well snow crab hear, as well as in recording natural feeding sounds, so that eventually we can examine how snow crab behavior towards feeding sounds is, and eventually we might be able to get out and do another catch per unit effort study with the appropriate sounds. And with that, I'd like to thank our funding agencies and partners, including SNOMAP and the Canadian Centre for Fisheries Innovation, as well as the vessels and crew of everyone who has helped us on this research. Are there any questions?
Thank you, Megan. Yeah, if you have any questions, you can raise your hand on the side there, or you can type it into the chat window.
I'm gonna ask a question. Megan, you mentioned the luminescent traps, and you mentioned that it was cost effective compared to other sources of light. But what about like the comparison of the cost of a normal pot without a light? Compared to this one with the luminescent trap, like it is too costly for fishers to implement?
Oh, not at all. So a traditional pot um, is typically around like $80, I want to say. and the glow pot can be purchased for roughly $5 more. So it's extremely cost effective. Whereas an LED, say, could be $50 to $100.
And you also talked about light in troll fisheries. Have you tried like here in Newfoundland? Are they using some kind of light on that, or like what kind of organism are you trying to catch or avoid using that light?
For which species, sorry?
For troll fisheries.
So there's lots and lots and lots of studies on the use of light in trawl fisheries. It's becoming much more common to attach lights onto different parts of a trawl in order to either attract species better or reduce the capture of other species. So it really depends on what species you're looking at, because as I said, as a bycatch reduction device, you don't want to reduce the catch of your target species. Um, so you have to make sure that you're affecting only the species that you want to affect. So in terms of uh, small fish like Ulican, um, which are a type of smelt, the lights on the fishing line, so right at the mouth of the trawl near the ground gear, are what cause the Ulican to um, sort of get out of the way of the trawl. Whereas if you put them inside the net near the bycatch reduction device, there was either no effect or you caught more Ulican, meaning they didn't actually go up through the escapement panel, they stayed in the net.
Thank you.
Anyone else? Well, if anyone has any other questions, feel free to shoot me an email and I'll be happy to answer.
Thank you, Megan, for coming.
Thank you for having me.
Thanks for all the listeners who joined in the seminar this week.